What is voltage? Well, I had some fun and made a 60-second crash course last week looking at how voltage is defined from a physics standpoint. There were lots of equations and stuff. It was nuts. I figured in this video we'd slow down and talk in more layman's terms. Less brain melting. So I've talked a little bit about voltage, current, and resistance already in this Learn Electronics for Beginners series, and we've even used Ohm's law. But it's time to dive a little deeper and make some connections between my most recent videos about electricity at the atomic level and the working terms we use to make the electricity go. This is going to be short and sweet, and I'm going to be a sellout and use an analogy that's probably been used for teaching this like a billion times. Okay, if you watch my brain melt video with all the equations, it ended by defining voltage as energy or work in joules divided by charge in coulombs. But what the heck does that mean? Let's break it down. Say you have a big old container filled with gasoline and we poke a hole in the bottom of it for frolicsome purposes. Well, we have a thing called static pressure head in fluid mechanics that represents the weight of the volume of liquid in a container on the base of the container. I talked about holding a mass above the earth and force equals mass and all that nonsense and how there's potential energy to do work in my fastest voltage definition video. Same idea here. Pressure is just force over an area. So the volume of liquid has a potential to do a certain amount of work. If we think of this container like a car battery, there's a total amount of work that a battery can do. Now, imagine as the gas container drains, it starts using the energy. Well, as the liquid level goes down in the container, we have less static pressure, aka less energy available. Well, voltage is the amount of energy available to move an amount of charge, and as we use the energy in the container up, our head pressure will decrease. You can think of charge as the volume of liquid in our container. In the case of a battery, as we use up the total energy in the battery, our voltage decreases and we move less charge, and our car battery dies and we get eaten by bears. I mentioned in the brain melt video that total energy doesn't affect electric current, aka the rate of liquid spilling from our container. Available energy per unit of charge does. As the container empties, we have less liquid, meaning less head pressure. The rate of liquid flowing from the container slows as the container empties. We'll talk a bit more about electric current in the next video, so don't forget to hit that subscribe button. Just for something to chew on though, we typically design electric circuits with a specific job in mind. Let's think in terms of our container analogy. Say we want to connect a pipe and use the liquid flowing from our container to turn a turbine connected to, I don't know, a very impractical weed whacker. This weed whacker requires a consistent flow of liquid to turn and do the job we want it to do. If our pressure drops as we use the energy from the container, what could we do to make the flow stay consistent long enough to get our yard done? Tell me in the comments. Okay, a couple more things to talk about. First, there are a lot of different names and equation symbols we use for voltage. Here are a few. They all basically mean the same thing and refer to the potential difference between 2 points. In our container analogy, we've been thinking in terms of draining the liquid from the base of the container. What would happen if we drained it from the middle of the container? There would be less pressure because there's less volume of water above that point compared to the lower hole. It's important to note that our 2 points can be anywhere. We could say that our difference in pressure is much greater at the bottom of the container in reference to the top of the container than it is in the middle in reference to the top. We're always measuring voltage between 2 points, a measurement point and a reference point. It's a little harder to imagine this analogy in a car battery since we can't exactly just poke a hole in it in the middle. Watch me.
Milky, smoky, explosive, acidy awesomeness. Woohoo!
Well, we could poke a hole in it. A car battery is made up of 6 cells, and we could measure any of those cells in reference to either of the external terminals if we didn't have this pesky casing in the way. I don't recommend doing this, by the way. Don't do it. Anyway, we'll dive into more applicational stuff down the road with safer methods. The last thing I want to do is connect how all this nonsense applies to the last couple videos about electrons and atoms and stuff. So in the last Learn Electronics video about what materials conduct electricity, we looked at band theory for solids and the valence and conduction bands. With conductors, the bands overlap, so it takes very little voltage to get electrons into the conduction band to start flowing in a conductor. In other words, if we start with an empty container with a hole in the bottom and put gas in the container, we get gas coming out of the hole right away. It takes very little pressure to get it flowing out. For semiconductors, there's a small gap between the two bands, and the size of the gap can vary with temperature. In any case, it takes a little bit more voltage to get the electrons moving. Think of it like putting a spring-loaded flap over the hole in our container. It'll hold the liquid in until we've added enough gas to the container to open the flap and let the gas flow. For insulators, the gap is very large and it takes a lot of voltage to get electrons into the conduction band. Think of it like a cork instead of a flap. Maybe that cork would hold and never let anything flow in the case of our gas container, but what if we put a cork in the bottom of something the size of a grain silo? Eventually, the cork would shoot out. This is essentially how lightning works, since air is an insulator. Alright, don't forget to smash that like button and subscribe for the next one. This is Life Me Lightning, bringing a little lightning into your life.
Hi, babe.
Hi, can I have this? Do you want to choose it?
Why is taking my soda?
You're spilling it everywhere.
Fine, bossy lady. I like that. It's only sticky. It just makes me better at everything.
Okay, take a drink. Careful with your finger.
It's be fine.
It's on this hand. This one.
I can't feel it. That means it's better.